Hey guys, in this video, I'm going to talk about the steps in fine-tuning LLaMA 3.2 Vision Language Model. So the use case here is to enhance the model capability in understanding visual features, which are Amazon product, and also textual information, which are their information in order to produce coherent descriptions. The dataset that we are going to use is the Amazon product description dataset by Philschmid. So here is how the data look. Each sample in this dataset consists of a list of keys, which are image, unique ID, product name, category, selling price, model number, about product, and then the descriptions. So here we are given the image of the product. Let's look at one. We are given the ID, we are given the name, category, selling price, and about product, and we aim to write a good description for the product. That will be our main goal. So here, let's go back to the notebook. First, you will need to install this dependency. And you also need to log in Hugging Face. If you don't have a Hugging Face access token, you will need to create one. And the way that I use to log in Hugging Face is I save my access token in a file config.json, this file here, and whenever I need that token, I will refer back to this file and get the token from this file. Let me show you how the file looks. So the file here is just a dictionary which contains my access token. Okay, let's go back here. So we will log in, and we will first download the dataset and see how it looks. In this case, I'm going to use 95% of the dataset for training and 5% for testing. So in the first line here, I simply download the dataset as a dictionary, and then I split out data so that 95% is used for training and 5% is used for testing. And then I return the train and the test data. Let's look at the first sample in the train data. Okay, so here if we look at the first sample in the train data, we have the image, which is a pure image. We have the name. Basically, we will be focusing on the image, its name, category, about product, and then the product description is like the labels that we aim to achieve. So in the next part, I'm going to talk about processing the data. In fact, from my experience, a major part in fine-tuning LLM is in processing the data. So first, we are going to check the header, system prompt header or user prompt header, whether it is in the current token list. The goal is we will not train on these header tokens because they are default tokens. So we are going to mask all these tokens by -100 so that they won't participate in any loss computation later. So here in this function check header target sequence, targets here can be either the prompt header, the system prompt header, or user prompt header. Let me show you what the system prompt header look like. I should have it here. So the system prompt header is this prompt here, start header ID, system, and end header ID. For user prompt header, it is start header ID, user, and end header ID. So we will look for these prompt headers, and we are going to mask them by -100 so that they won't contribute to the computation of the loss. So here we loop through the sequence, right? And we check whether these three tokens is either the system prompt header or the user prompt header. If it is, we return true. Otherwise, we return false. And here in this function, we will replace all these headers all the tokens in these headers by -100. So yeah, so whenever we have a target in the sequence, we replace them by -100. So here is the prompt that the user is going to provide to the model. So the prompt is create a short product description based on the provided product name and category and image. Note that the image is not provided in this prompt because it is a part of the processor that I will talk about later. Only return the descriptions. The description should be SEO optimized for a better mobile search experience. And here we have a placeholder for product name and category. The system message here is you are an expert product description writer for Amazon. So this system message will always be included in the beginning at the system header. So this is like to assign a role to the system, a role to the LLM, and telling that it is an expert product description writer for Amazon. And next, we are going to format the sample, each sample in the dataset. So for each sample in the dataset, we will replace all these holders here by the product name and category. And then the formatted prompt here will be, we will start with begin of text. We start with the system header, and then the system message, which is an assignment for the role for the system. In this case, it is you are an expert product description writer for Amazon. And then we always end with this EOT ID, which is end of turn ID. So every time we finish the assignment to some role, we include EOT ID, end of turn ID. And after the system message, we will start with the users. So we start with the user header, and the formatted prompt here will be the prompt that the users give the model, right? And we also start with an image token. So this is the image token to tell the model that we include an image, in this case as an input, and then we end it with end of turn ID. And then for the model to learn, we will start with the header, assistant header, which is basically, this part is basically tell the model to start generating the answers. But here, because we are training, we will provide the answer to the model, right? So we will provide the description to the model. And description in this case is from the train sample. And we finish with the end of turn ID and also end of text because we end here. And then we return the formatted prompt. So now this will be the prompt that is given to the model. Now we are going to talk about how to tokenize text and image using the processors. So in this function, we will aim to process the text image pair, and also we want to mask the unnecessary things like header or the image token, which is this token here, by -100, because these tokens are not going to participate into the computation of the loss. Right? So here we start with the text prompt from no. So here by default, the processor always include the begin of text in the beginnings. So I will replace this begin of text by an empty string, because if we keep this formatted prompt here with the begin of text, then the processor will add another begin of text which is redundant. I mean, an easy way will be not to care about this, right? We delete this, and then you don't even need this line here, but because I already write the code and already run it, I don't want to run it again. So here we will take out the beginning of text because the processor later will add the beginning of text automatically, and we are going to process a batch by putting the image and also the text prompt. We specify that padding is true and return tensor type is PyTorch. So here the processor take in the input as the image, the prompt, that the formatted prompt that we just look at here, and also the padding. So now we will basically try to mask all the tokens that are not participating into the computation of the loss by -100. And here label list, I start with the empty list. So we loop through all the data in the batch, so that can be extracted from the input ID. So we loop through all of them, and we extract the prompts, which I call dialog tokens. We convert it to list, and here for the labels, I just create a copy to avoid modifying the original dialog tokens. We will get all the indices which has the form end of turn ID, right? So this end of turn ID has ID 128009. So we will extract all the token with value, all the index of the token, with the value 128009, and then we are going to extract the part where we have all these system header or user header, right? And note that here are the ID of the token of the system header and the user headers. So whenever we see these IDs, we will mask them to -100. So note that each of these header also end with the end of turn ID, right? That's why we are extracting all the end of turn ID. So here we loop through all the indices for the end of turn IDs, and so here we are looping through like a chunk of them, right? So each sequence that we consider will be from the last one to the current one, and we check whether any of these headers is in the current sequence. Yeah, so if any of them is in the current sequence, we should mask with -100, because if something is found, this sequence should be masked because they are not going to participate into the loss. So the only part that is going to participate into the loss is the generation of the model. And if you look back to this formatted prompt here, this part here, the description here will be the part that participate in the loss. Everything else that come before it should be masked to -100. All right, so if we found, we mask to -100. If we don't, we increase the index. And we also don't want the tokens in the assistant header to participate in the loss. So we will mask all the tokens which appear in the assistant header by -100. These tokens have IDs that I already list here. So we replace all these tokens by -100. And finally, we will mask all the padding token and the image token by -100. And note that the image token in this case is 128256. And then we form a new labels for our batch. The last part here is a data collator. Basically, it tells the trainer how to collect all the corresponding text and the corresponding image together in order to tokenize them and get the input for the model. Here we init the processors, and we also specify that the processors have tokenizer with padding size to be the right size. In the call functions, we simply we have the samples as the argument here. Each sample is a pair of text and image. So we will loop through all the sample. We extract the image, convert it to RGB, and append it into the image list. So let me rewrite this so that it's easier to see. For the text, we will format the text by the format data function above. Well, let me see where the format data function. Yeah, this is the format data functions. So we will format the text and then append the formatted text into the list. And finally, we run the tokenized functions on these formatted text and image using these processors. So the final answer here will be a batch of inputs which are input tokens which will be fed into the model. So now we are ready to download the model and train it with PEF, which is the short form for parameter efficient fine tuning, if I'm correct. So here we will need to import auto model for vision to sequence auto processors, bits and byte config. Here we specify the model ID and also specify the quantization format. So here I'm going to load in 4-bit with the quantization type NF4. So this is used in QLoRA. And here we load the model using auto model for vision to sequence from pre-train. So we just need to put in the model ID. Device map can be auto. Here I am running on a GPU, so it will be automatically loaded to my GPU. We specify the data type, the quantization type, and token. For processors, we will load it using auto processors. So here, yeah, I already load the model, and actually I already train it. The training takes quite some time, so I train it before making this video. Alright, so this is basically the raw model. Not sure whether it's a good idea to load it again. It will take some time, so yeah, probably not a good idea. So this is the raw model, which has 11 billion parameters, and I certainly don't have enough computation power to fine-tune this whole raw models. So the fine-tune technique that I'm going to use is called LoRa. If you have watched my last video, you already know what is LoRa, but let me just make a Google search here, LoRa, and try to explain it to you again. LoRa fine-tune LLM. Okay, this is the image that I need. So in LoRa, if you look at this image here, let me make it maybe a bit bigger. So in LoRa, it basically replaces each of the linear layers. So let's say the original linear layer has dimension d by d. It will add another layers into this original linear layer. So for the new layer here, it is added parallel to the original new layer, and it is a combination of two linear layers. One has shape d by r, and the other one has shape r by d. So it will add this layer and freeze the weight of the original linear layer and make this part, the weight of this part trainable. In other words, in this case, the number of train parameter will be d times r plus r times d, which is 2 times r times d. and R is much smaller than D. So compared to the original model where the total number of parameters, trainable parameter is D squared, now our total number of trainable parameter is 2RD. So the smaller R is, the more we can save in terms of the number of parameters. So here, why do we still keep this original layer in our model, which means the LoRa model? So the reason for keeping this original layer is so that we still can retain the knowledge of the old models. So all the knowledge of the pre-trained model are stored in these ways. So by keeping them, we still keep the knowledge of the original model. And this is the part that we are going to instill the new knowledge in. And that is basically how LoRa works. And in order to initiate LoRa, we need to specify the parameter R here, and also another parameter which is called alpha. Alpha is a factor that specifies the weight for this part. So here the standard initialization is alpha equal to 16. We also have dropout, and here I set it to 0.05, which is the parameter in the original paper. We don't use bias for these linear modules. For target modules, here we can choose which type of module that we want to apply LoRa, and here I just choose Q projection, K projection, V projections. If you want to explore further, you can also use the output projection, gate projection, up projection, or down projections. And now we will set the training arguments. So here I import the supervised fine-tuning configuration from TRL. We specify the output directory, set the number of chain epochs. The chain batch size here I set to 2, but I keep gradient accumulation step to 8. So basically, if you have good GPU with more memory, you can increase the chain batch size. Right? But in this case, even though I set the chain batch size to 2, I set also the gradient accumulation step to 8. So this means I only compute or update the parameters of the model after 8 steps. That means theoretically or practically in this case, my batch size is 16. Even though I don't have a GPU with high memory power, by setting the gradient accumulation step, I have increased the batch size by 8 times. I also use gradient checkpointing. Locking step means I will print out the arrow, the train arrow for every 10 steps. And the other parts here are more or less standard, right? Yeah. So these are the training arguments. And also I remove, I don't remove unused columns. And now we will set up the trainer. In this case, we will use the supervised fine-tuning trainer from TRL. So to set up the trainer, we simply need to put in the model, the training arguments, the train data, and also I specify the data collector and the configuration for LoRa, which is just now the parameter alpha and R, and also the tokenizers. Here I specifically move the model to LoRa, but I think this sentence is not even necessary because the model is loaded with device map equal to auto, and in this case it should be in GPU, and then I hit train. I already trained this, and this as you can see it takes about 2 hours. Yeah, and here you can see the log of the training loss, and the loss go down. That's a good thing, right? Okay, and then after that, I will save the train model using trainer.save model in the output directory. In this case, it is output directory. So when we do this, if you recall my last video, I do the usual way of saving the entire state dictionary of the model. And in that case, what is saved will be the whole model together with the LoRa layers, with the additional LoRa layers. And that will be huge, right? However, in this case, by using this method, we only save the LoRa weights. So this will be much less as compared to saving the whole model. I'm going to show you later what is the number of parameters or how many LoRa weights that we save in our model. And also we free the memory by deleting the trainer and the model and empty the cache. So now let's do inference. First, we will load the train model. And here I also load the base model and for comparison. So here in this load fine-tune model, I put in the base model ID, which is LLaMA 3.2 vision model. Adapter path is the path that I use to save the fine-tune model. Basically, these contain the LoRa weights, and I load the processors with the base model, and then I load the fine-tune model. So first, I create a copy of the base model, and I load the LoRa weights into the fine-tune model. Then I return both the base model, the fine-tune model, and the processors. Let me print out the sums of parameters in each of the models to show you the number of LoRa weights that we train on. For P, okay. I need another bracket. Let's put comma here to separate the numbers. And also print out the, I guess this is a bit small for you. Okay. Also print out the fine-tune model. But here we want to print out those that requires gradient. P dot require grad. Okay, let's load the models. So it will certainly take a while, especially for the base model to be loaded. Hopefully I don't make a typo here. Now the model is loaded, and let's look at the number of parameters here. Here, unfortunately, we get 0 parameters for the fine-tune model. The reason is because when we load the model adapter like this, where the fine-tune model just load the adapter like this, it has already put the model to evaluation mode. So there will be no more trainable parameters. Well, let's see how I can still print out. Maybe let me define, let me just print out the total number of parameters and then subtract it by the number of this number in the base model to see how many trainable parameters are there. So here, let's just define two numbers. Right? This is B. Well, A will be the number of parameters in the base model. And let's see what is B subtract A. Well, So here we have about 8 million trainable parameters. That means there are this number of parameters for the LoRa ways. All right, now the final part is to generate description based on the fine-tune model. So here to do this, I start with again the prompt that we used earlier. Let me make this a little smaller. So create a short product description based on product name and category, only return description and so on. So here product name, we have the placeholder for product name, and so is category. System message is you are an expert product description writer for Amazon. So the generate function take in the model, the sample, which is a sample case, some type of Amazon product, where this sample is a dictionary which contain the name of the product, the category, and its image. And also we need the processors. Here first we will format this prompt using the name of the product and its category. And for the formatted prompt here, we start with begin of text, user header ID. This should be systems. There's a typo here. It should be systems and its message. And then we start with user header ID and the message from the users, followed by the image token. And then we end with this assistant header ID. So in LLaMA, whenever we specify that this is the end of the input to the model, then we tell the model to start generating response. And then here we will extract the image, and in this case, the image data type can be either a direct URL or it can be a byte image. So in this case, we will in the case of direct URL, we will need to get the bytes of the URL in order to put into the processors. So for the processors, we will put in the image, the formatted prompt, and then the processor will give us tensors that can be used as the input to the model. So here we move to the correct device, and then we start the generating using model.generate. So here we simply specify the maximum number of tokens that we would like to have, temperature, top P, and do sample. And so when we do all these, then the output will contain this formatted prompt in this form, and also the generations of the model. So here we don't want to keep this. We only want to keep the part that the model generate. So we will trim the generated IDs by taking out the in IDs. Here is the length of the formatted prompt, and we take out this part and we only keep the part that the model generate, and then we decode this part to get the text. It looks fine. Let me just run it. So here I take a sample from the test data. This is the data that the model never see before because we only train on the trained data. So for this particular sample, I will generate. I will first write out what is the ground truth descriptions by Philschmid from the dataset itself. I also generate the description by the base model and also description by the fine-tune model, and then we will compare these three descriptions. DS test is not defined. Just now I get disconnected to the GPU, so I need to reconnect and didn't run this part. Okay, so now I should be fine. Let's go here. So here first I display the image. Let's see, this is the ground truth descriptions. And this is the base model description. It doesn't look good at all, right? And this is our fine-tuned model description. Unleash your child inner. Start with kids on stage. This pretty much, the first sentence here pretty much looks similar, but the second, but after this, it is different. Yeah, I can see if we compare the base model and the fine-tuned model, there is obviously an improvement in the generation. Let's look at another example, and in this example here we have the Superman product, and here I will only compare between the base model and the fine-tuned model. It takes a while. Alright, so here it is. So the base model description is, I guess it's not that nice, because if you see the last part here, it's not nice. And for the fine-tuned model, it looks much cleaner. Yeah, it sounds good. And lastly, for the last part here, I get it from the script by Philschmid himself, where he fine-tuned this, where he fine-tuned 1.2 or 1.5 on this same data set, and I find it very useful. So he basically put the two descriptions together and compare them. So this is from his script, and we will just put the two descriptions and then compare them, and maybe in this way we can see a clearer improvement from the base model to the fine-tuned model. So that is also the end of my video, and I hope you have a better understanding on how vision language model work, and I hope you enjoyed. See you next time.